All right, welcome, young astronomers. I hope you're having a good evening. Tonight would be a perfect time to go out and look at the sky. I was out last night. Mars is in our night sky, so you have another planet to add to your journal if you like. And Jupiter is super bright, so go check out the sky tonight. We're gonna finish off tonight. We're going to finish off our lecture on how the solar system and other star systems were formed. Before I get going, are there any questions or comments about anything? All right, let's get on with it then.
No, I'm in class.
Is that a question from somebody? I heard somebody, but barely. If that was a question, please speak up. If not, mute your microphone. Okay, so the nebular theory. The nebula, remember, is a large collection of dust and gas. And here is actual observation of the nebular theory, not an action. This process that we're going to learn about tonight, the shrinking of the cloud under gravitational forces, takes millions and millions of years. So we can't watch a video of it, but we can see it in different stages. And we see baby stars and baby planets invariably are being born in these clouds of dust and gas. That's why we call it the nebular theory. And we saw some beautiful pictures of that. Remember the baby stars, what's called a protostar, actually emits infrared light, not even visible light. And then when when nuclear reactions turn on, they emit visible light. And we're going to learn in a couple of weeks that the color of that light, we already know that is dependent on the temperature of the star. But what we haven't learned yet, I mentioned it briefly, and I'll mention it again right now, is that the hotter a star is, means it's more massive, and it doesn't live very long. So when we see these blue stars, we know those are baby stars because unfortunately these stars don't live past being babies. Some of these live for only thousands of years, whereas stars like the sun live for billions of years. And so we see these blue stars are not just are also in these nebulas. It gives us further evidence for our nebula theory. Something is going wrong here. Okay, we talked about where we were born. I'm not going to go over that again. So we need to do the physics of a gas cloud. So how do we characterize a typical gas cloud? One is by what's inside of it, the composition, hydrogen, helium. In fact, the first gas clouds in the universe, that's all there was. But as through this recycling process of stars, heavier elements were made and shot out into the universe in clouds of dust and gas. And so each time one of those stars dies, it makes a gas cloud that has more elements in it. For instance, water. Now, not in its liquid form. In outer space, there's no such thing as liquid water. It's either ice or it's a gas. The liquid state, you need some kind of atmospheric pressure to keep something in the liquid state. We don't really have liquid water, but we have either gas or we have ice, and then dust, silicons, irons, all sorts of metals, particles of that. So we also the number of particles there is a characteristic of the cloud. Its temperature is another characteristic. You know what temperature is, but you may not know what temperature is on a microscopic level, and why that's what's important to us here. Temperature is really it's a measurement of how fast the particles are moving, and that the temperature in a room is really how fast the air molecules in the room are moving. They're moving at hundreds of miles per hour, by the way. But even the temperature of a solid. You may not think that the particles are moving in a solid. You may think, they're in a crystal lattice, but they're vibrating. And so that's the hotter something is, that means the more the particles are moving. And then the volume is the size of the cloud. And then the pressure. The pressure is kind of how many times the particles hit each other or you. You may notice, especially if you've ever gone to like Florida or something, you can kind of feel the atmospheric pressure is heavier there. It's not really heavier, it's just that you're getting hit by those air molecules more than you would be otherwise. So pressure is about the number of collisions. If you've ever taken a chemistry class before, I'm not going to test you on this, but you learned the ideal gas law. PV is equal to nRT. The pressure times the volume is equal to the number of particles times some constant of nature called the Boltzmann constant times the temperature. So we're not going to do any math. I mean, it's pretty easy math, but we're not going to do it. But you do need to understand the relationships between these. Because usually in a gas cloud, the number of particles is a constant and Boltzmann constant is a constant. So there's this relationship between the pressure, volume, and temperature, which you inherently kind of know this, blowing up balloons and things like that. But when the volume decreases, the pressure increases. This is the one that's important to us in astronomy. And when the pressure increases, the temperature increases. Okay, so that's forget about the math for this anyway. All we need to know is when something shrinks, the pressure increases. So thinking you have a cage of bees, and they're minding their own business, but as we shrink the volume, they're going to hit each other, whether they want to or not. They're going to, the pressure, remember the pressure is how many collisions they have, is going to increase. And as the pressure increases, the temperature increases. Sticking with the bee analogy, as they hit each other, that kind of can make them actually go faster. Remember, pressure is the number of collisions, and temperature is how fast the particles are going. And in a large nebula, there's a constant fight between gravity, which is trying to shrink everything, not just gas, but gravity is trying to shrink anything. Remember, we learned gravity is a mutual attraction between any two massive objects. Even these grains of tiny particles are attracted to each other by gravity. Not very strong, but it's there. And over millions of years, a gas cloud will collapse. What keeps a gas cloud from completely collapsing is the pressure. The stuff inside of it, as it hits each other, it keeps things from collapsing. Like when you blow up a balloon, you're putting more particles and more pressure in there. That will keep that'll keep gravity from squishing the balloon down. Pressure is trying to make the volume bigger, and the gravity is trying to make the volume smaller. And it's this constant battle. We talked about this already. In order to do calculations, we need to do this for Wien's law. We need to do this to understand gas laws, how these nebulas are. We cannot use Fahrenheit, and nobody besides the United States uses Fahrenheit. But we even can't use Celsius. We have to use the Kelvin temperature scale, which corresponds to zero movement of the particles. Neither zero and Celsius or Kelvin work. If you ever need to do a conversion, those are the conversion factors. Kelvin is just Celsius plus 273. And then to get to Celsius, you can use, if you're given Fahrenheit, you do that. I'm not gonna, the important, it turns out, as far as studying solar system, planet formation in particular, the temperature that is important is actually the freezing point of water, which is 32 degrees Fahrenheit, 0 degrees Celsius. We don't care about that. It's 273 degrees Kelvin. So keep that in your head. That is an important piece of information to understand the solar system, at what temperature the water freezes. We'll skip that. We already did that. So let's talk about that self-gravity. Why do we talk about how asteroids aren't planets because they're not massive enough. Now they have some other things besides pressure that holds them up that we'll talk about next week. But if we just have we have a cloud of dust and gas, why does it shrink? Like, why doesn't it pull equally on every side? And it does in the center. But the reason why it shrinks is that if we look at we take a couple of little boxes of gas here, we can see that they're getting pulled in all directions by the stuff inside. But if there's nothing on the outside, nothing is pulling it on the outside. And so these gas clouds will eventually collapse. They'll shrink and collapse. Again, these aren't very massive, and gravity is relatively weak. If we were all on an ice skating rink right now, and there would be a gravitational attraction between all of us, but the people on the outside of the rink would not feel it. There's no spectators now, especially in COVID. So there's no spectators out there, so they're going to get pulled towards the center. And so with people, it would really, if you just stood there and there was no friction, after 1 million years, we would all be in the center of the rink. And the gas clouds are easier to move. There's less gravity because they're less massive, but that also means they're easier to move. They will collapse, but it takes a long time for them to collapse. If it was a stationary gas cloud, they would actually completely collapse into what's called a primordial black hole. We talked about on Monday. But in general, the gas usually is not stationary. It's usually swirling around, and just like swirling around, the moon has some perpendicular motion that keeps it from crashing into the Earth. This gas cloud, if it has some sort of rotation, that will keep it from completely collapsing. It will still collapse, but this gas cloud is going to kind of get segregated into different regions that are kind of spinning, and they're going to collapse. We call these molecular cloud cores. And each one of these is going to turn into an individual star system with one sun or two suns. Not just one. 60% of the stars in our sky are actually binary star systems where the suns are rotating around each other, and they have planets rotating around them. We didn't mention this, but our Proxima Centauri, right? We've talked about it several times now. Our discussion about aliens and who they think is the president. That star system has 3 stars and 2 planets that we know of. Probably has more planets, but it has at least 2. But it has 3 stars orbiting around there. So it's kind of a cool configuration. So each one of these is going to turn into some sort of a star system. and it's going to continue to collapse. This disk formation, it's going to flatten out into a pancake. And it's going to start to spin faster and faster as it shrink. This is conservation of angular momentum. It's the same reason when a figure skater starts their spin with their arms out, they go slow. And then they, as they pull their arms in, they'll spin faster. So that's why it goes faster. The flattening of it is, I don't know if you've ever messed with clay. You put clay on a turntable and it's wet enough, it'll actually flatten out into a pancake. Or when the pizza person is making your pizza and they have the dough, it's in a sphere. They start to rotate it, it flattens out. It has to do with the probability of collisions and whether that collision is going to help you go into the right direction. So these things are all kind of moving this way. It's kind of like trying to cross traffic in 3 dimensions, right? You try to run across a highway, you're going to get hit, and it's going to make you go in that same direction. So eventually, everything will be going in the same direction. But as the nebula flattens out and gets smaller, the core gets hotter. Because the volume shrinked. The volume of our cloud is now smaller, so that means the pressure is increased, and that means the temperature increases. And that is most pronounced in the center of the cloud. And so we get a clump, and actually we get this clump, it actually kind of retains its spherical shape in there, and while everything else flattens out. It's getting hotter. Well, before we consider that, I mean, those are all animations, but these are actual images of other star systems where we can kind of see this disk forming in there. And so we observe these disks around other stars in the system. It's going to continue to shrink and get hotter and hotter. It's going to convert gravitational energy into thermal energy, and the center of that is going to gravity is going to keep trying to pull in. The volume is going to shrink. The temperature is going to get hotter, and finally we will get what's called a protostar. We'll get the meatball in the pizza. It's much more dense than the disk, and it's getting hotter and hotter. It's what's called a protostar. And here's some images of protostars in another nebula, infrared images. We can see these are the baby stars that are being born. We can actually simulate that by knowing all of the laws of physics and gravity and gases. We do a supercomputer simulation of a gas cloud, and as it collapses, we can kind of see this structure starting to form, and we will start to see little baby protostars being born in the gas cloud here, and we can kind of see how it kind of rearranges the gas cloud as it goes along, and so this looks pretty much like this is for 3 stars. This looks a lot like our nebula with the protostars in it, right? It looks pretty much like that. I mean, that's not the only reason why we believe that model, but that's a good, our models are actually producing the nebulas that we see in there. We can do better than how it looks. We can actually use the Doppler effect to measure the rotation of these gas clouds in regions where there's lots of star formation going on, and we can see, remember, the red part is moving away, the blue stuff's coming towards us. So we can actually measure the rotations of these gas clouds around the protostars. Here's just some more close-ups of that, pillars of creation, that show you these protostars. Here's another one, the molecular cloud in Perseus. Again, looks very much like our simulation. This was taken by the Spitzer Space Telescope, which is sadly ran out of juice, but was our best infrared telescope. It's going to be replaced by the James Webb, hopefully in the next year or two. There's a balance between the temperature and pressure, right? That's what's trying to make this expand, and gravity. But gravity is going to win. It keeps shrinking and keeps shrinking until it gets hot enough in the center. As it shrinks, it keeps getting hotter and hotter. So notice this, one thing that people have trouble with, because we're used to babies being smaller. Protostars are much bigger than regular stars. So there, it's actually, the star is, the protostar shrinks and gets hotter and hotter until we say the magic happens. The core of this gets hot enough for nuclear fusion to occur. And we will have a whole chapter that describes that process. It's really taking 4 protons and squeezing them together under this incredible pressure and temperatures, and they fuse and make a helium nucleus, and that releases energy. But protons don't like each other, so you have to get it really hot and have a lot of pressure for that to happen. And again, we'll go into more detail on that in a couple of weeks. But a star, literally, the core explodes. A nuclear bomb. In fact, trillions of nuclear explosions per second are going off in the core of a star. We consider this the birth of a star. Before that is a protostar. When nuclear fusion turns on, it becomes a star. And it starts to emit mostly visible light. Before, it was emitting infrared light, and afterwards it emits visible light. Let's look at another quick simulation of that now with a much larger gas cloud, a much bigger computer, by the way. These computers, they fill up a whole building of separate little units, which put together is called a supercomputer. We can kind of see a molecular cloud turning in. The white is when they turn into stars. And you can see it's kind of like popcorn, that when you make a star, it actually kind of makes the gas spin up a little better, that's faster, and that makes another star. So it kind of makes this popcorn effect. Once you get a couple of stars born, we get many, many born in the same area. Also notice that some of those stars leave the cloud, like we did. Remember, we don't live in a cloud anymore. We don't live in a cluster anymore. We see old star clusters that don't have any gas around them because they've used up all the gas. But we live in neither. But you can see in this simulation, many of these stars are shot out of the region. Again, here's another star cluster. This cluster doesn't have a lot of gas. This is a very old star cluster. Notice there's no blue stars in here. They're all yellow or white. This is a very ancient cluster. It's not making stars anymore. So when the star explodes, it doesn't just emit light. It ejects a lot of material, protons and electrons, what's called the solar wind. And the sun, we'll learn, actually still has a solar wind. It's much less now than it was before when it was born. But some of that gas gets pushed out this way, and then especially the charged part of that material, because the sun is spinning, it actually has a very strong magnetic field. It ejects that material out into space in the form of these jets. So it has just kind of a radial wind, and then it very often will have 1 or 2 jets spewing that out. And here's a simulation of a protostar turning into a star. Here's an actual image of one. Here's another image of one. Here's another and another and another. We see these jets of material all throughout the galaxy when stars are turned on, and more. And I could show you pictures of these all night, but I won't. But we see these jets, more evidence for our model of how stars are formed. You will notice this band in here, which is kind of blown up again if we look at over here. The star is not this barbell shape. The star is this size, but it's still surrounded by a tremendous amount of dust and gas, which you can't see through. And so it's actually blocking the light. The light from the star would look this size, but the gas surrounding it is blocking that light. And that is where the planets actually form. At the same time, they're already starting to form a little bit, but they continue to form after the star turns on. So how do planets form? I mean, it's kind of the same. It's kind of the same thing going on there, but right, it's not concentrated in the center. So gravity's not trying, and these things are really, really tiny. Gravity isn't strong enough to really get this process started for them. It is for the star, but for the planets, we need something else. And for the longest time, we didn't actually know what it was. You know, the particles hit each other and they get closer. Some of them will stick together. And as they stick together, they get bigger and eventually they'll get massive enough to start attracting other things. But it turns out it's like static cling. It's static electricity that causes that initial sticking together of the little pieces of dust. Again, this is what the Earth started at. It was a tiny little grain of dust, and it smacked into a bigger grain, and it smacked into a bigger grain. Right? Remember that picture of the well, let's not remember it. Let's look at it. That picture of the asteroid we saw on Monday. Those little grains stuck together, right? This is what I meant. This is the poster child for nebular theory on how planets formed. They first stick together with static clinging, and then when it gets big enough, gravity will hold that thing together. All right. We actually can do an experiment on the ISS to actually see this in action.
Here we have a gallon-sized plastic bag filled with 1 millimeter diameter sodium chloride crystals. You shake this up, and the individual crystals will rapidly form agglomerates, and these in turn form floccules of the order of several centimeters on a side, and all of this happens in about 10 seconds.
So notice it's all separated, but then the static electricity starts to make this stuff clump together. You can watch this whole thing. They do it with coffee. They do it with all sorts of different things. But that's what got the planets started. So let's talk about our particular gas cloud for the solar system. They're all a little bit different, as I said, but the solar system's nebula was made out of mostly hydrogen and helium, as we would expect. Remember, those are still the most abundant elements in the universe. Makes up 75%. I'm sorry, it makes up 98% of the universe. 75% of that is hydrogen, 25% of that is helium. But there's other stuff. In our particular gas cloud, we had a lot of water. We had methane and ammonia. This was in these crystals, these ice crystals. We had rocks, silicon, compounds, and we had metals. Particular in our nebula, we had a lot of iron and nickel and aluminum. And you can see kind of the ratios here. This will give you an idea of why the rocky planets are so much smaller, right? Rocky planets are made up of only 0.4% of what was in the nebula. The gas giants are made out of hydrogen and helium. They had a lot of material to work with. And the sun is made out of hydrogen and helium. Remember, the sun has almost all of the mass of the solar system. The sun also has these elements in it as well, in its atmosphere, and its surface, in quotation marks, but it's dominated by hydrogen and helium. So, but why are the rocky planets near the sun and the gas giants are out here? There was certainly a lot more hydrogen and helium closer in. The density of the gas cloud, it's really lots of material in the center, and as you get further away, there's less material. well, why in the world would Jupiter be so big? It's a lot further than the Earth. And that is because, first, two reasons. One is the temperature of the sun was so hot that all of the water all of the ice crystals in the inner part of the solar system, once the sun, even before it exploded, but once it got hot enough, it all evaporated into gas, and that solar wind pushed it out to the outer part of the nebula, the outer part of the disk of the solar system. So only thing that could survive close to the sun was the heavier stuff and the stuff that does not melt. And that is silicon, that's rock, and metal, right? You can melt ice a lot less temperature than you can metal and rock. And so that explains why the inner planets are made out of the material they are. They're made out of rocks and metals, and why they're so much smaller. And the reason why Jupiter is so big, Jupiter actually formed on what's called the ice line, this 273 K. When the temperature from the sun got down to 273 K, which is basically, it's minus what? It's minus 290 degrees Fahrenheit. It's really cold out there. No, I'm sorry. It's 0 degree. I mean, it's 32 degrees Fahrenheit. Once it got out there, once it got that cold, the water vapor, the gas state could form back to ice. And so Jupiter kind of was like a giant snowball packed together. Whereas we're trying to make, first of all, it's harder to pack metal and dirt together than it is ice, right? So we can, it's easier to clump together. There's more material, and it got bigger and bigger. And then it's got all this gas around it, the hydrogen and helium that the solar wind blew out of the early part, the inner solar system. And that is why Jupiter is so large compared to these. And then the rest of these are a little bit smaller, but they're also large. There's just more material now after the sun turned on, and less volatile. I mean, it's less temperature, so it can survive in the solid state out here instead of gas. We call that the frost line. There's actually a couple of frost lines. There's another frost line that distinguishes, the water frost line is kind of why we have the gas giants, why we have Jupiter and Saturn. They got big because of water ice. There's another frost line, which is kind of the organic material frost line. The temperature with methane and ammonia and carbon monoxide freeze a little bit colder. And out there, we don't just have water snowballs, we have methane snowballs and ammonia snowballs and carbon monoxide snowballs. And so we have that's why we call these the gas giants out there. They're able to get big enough out there. And so it's really the temperature of the sun that makes the segregation of the planets into the 3 different classes we have. I said all that. But let's look at this in a little bit more detail. If we look at the temperature and the amount of material in the disk, there's a problem with this. The problem with this is there's really not enough material out there to make Uranus. And notice Neptune's not even on this picture. There's nothing out. There was no material in the protoplanetary disk where Neptune is right now. So how do we make a giant planet out there where there's no gas and dust? That was one of the first problems with the nebular theory. There just wasn't enough material, even where Uranus and Neptune are, to make planets. And also remember, Neptune is actually more massive by a little bit than Uranus. So not only wasn't there enough out there, but it was more, somehow Neptune got more material than Uranus did. So here's our first little kind of, clink in the armor of the nebular theory. Why in the world? How did we make these 2 ice giants? It describes everything else really well, right? It describes why the rocky planets are so much smaller and why they're closer to the sun. It explains why Jupiter and Saturn are so big. It has a hard time explaining the existence even of Uranus and Neptune. I think I said all that. I did. Here's just some more pictures from other star systems of those protoplanetary disks. This is ALMA, the other observatory in the Chilean desert that actually observed those things. So we have time. Let's watch this video, at least part of it.
A new ALMA image has revealed extraordinary fine detail that has never been seen before in the planet-forming disk around a young star. These are the first observations that have used ALMA with its antennas at almost their maximum extent. This has resulted in the sharpest picture ever made at sub-millimeter wavelengths. The new results are a huge step forward in the observation of how protoplanetary disks develop and how planets form. This is the ESOcast, cutting-edge science and life behind the scenes at ESO, the European Southern Observatory. ALMA, the Atacama Large Millimeter Sub-Millimeter Array, is the world's most powerful telescope for observing the cold universe. It consists of 66 high-precision antennas that can be placed in different configurations. For the first time, the ALMA array has now been configured with the antennas up to 15 kilometers apart. This is close to the maximum possible baseline of 16 kilometers and allows ALMA to discern much finer detail than has ever been possible up to now. For ALMA's first observations in this powerful new mode, researchers pointed the antennas at HL Tauri, a young star about 450 light-years away, which is surrounded by a dusty disk. The resulting image exceeds all expectations and is sharper than images routinely obtained by the NASA ESA Hubble Space Telescope. It reveals unexpected fine detail in the HL Tauri protoplanetary disk, which consists of material left over from the birth of the star. The image shows a series of concentric bright rings with enigmatic dark patches. These structures are clear signs of the presence of multiple planets as they sweep up material from the disk. HL Tauri's disk appears to be a lot more developed than would be expected from the age of the system. This suggests that the process of planet formation may be faster than previously thought. Young stars like HL Tauri are born in clouds of gas and fine dust, in regions which have collapsed under the effects of gravity. Dense hot cores form and eventually ignite to become young stars. These baby stars are initially cocooned in the remaining gas and dust, which eventually settles into a protoplanetary disk. Through many collisions, the dust particles will stick together, growing into clumps the size of sand grains and pebbles. And ultimately, asteroids, comets, and even planets can form in the disk. The young planets will then disrupt the disk and create rings, gaps, and holes, such as those structures now observed by ALMA. The investigation of these protoplanetary disks is essential to our understanding of how Earth formed in the solar system. Observing the first stages of planet formation around HL Tauri may show us how our own planetary system may have looked during its formation more than 4 billion years ago.
Okay, so that was a good review of everything I just said in English with some other pictures on there. If you didn't catch that, these rings are where planets are either full-size planets or what we call planetesimals. And as they orbit around, they suck in all of the other material, and that makes the planet get bigger and bigger and bigger until there's nothing left here. This is what we call clearing its path. And this is actually, we'll learn, this is one of the reasons why Pluto isn't considered a planet anymore, because it never did that. It lives in around a bunch of junk. All of the other planets, we don't, there are still some random, asteroids or close to us, but in general, there's nothing around our orbits. So I just saw this question. I don't know what. Red asks, why do they shoot off once created? That has to do, I assume you're talking about the star formation.
Stars. Yes, correct.
So, I mean, you can, again, it's kind of gravity holding it in. If you get something going fast enough, you can escape that gravitational force. So maybe you have one star explode over here, and that makes the gas move a lot faster. It's really, if it gets going fast enough, the star can get thrown out of the cluster. But good question. All right, so let's have some other, let me get rid of this. Just some other images of these planetary disks forming. Here's actually, we can actually see a baby planet formed here. And you can kind of see the gap. It hasn't cleared its path yet, but you can kind of see that it's started to make one of those rings in there. Again, the star here, this is an infrared light, but the star still emits a tremendous amount of infrared light. So we have optical instruments that make an artificial eclipse that will block out the light from the star, and that allows us to see the gas and dust. And in this case, we can see a baby planet being formed. So again, that's kind of, they start off smaller. As they clear their paths, the planets get bigger. So this is how we ended up with the 8 or 9 planets in our star system, in the solar system. Here's another image of another star system that has, we can see the ring disk, and we can actually see a little planet in here. We'll come back to this. This is an interesting system here. But so we see baby planets, we see protoplanetary disks surrounding stars all over the galaxy. This kind of we call this accretion. When an object gets bigger because things collide in it, we can kind of see the results of that. The craters on Mercury and the craters on the moon are results of these objects clearing their area through space. You may ask why we don't have those craters on Earth. We do in a few places, but our crust is recycling itself. So believe it or not, the Earth's crust had just as many craters in it 4 million years ago as the moon did. But through erosion and volcanic eruptions, the traces of that are erased on there. Here's some impact craters on Mercury. This is as Mercury was getting bigger. It got bigger by things smashing into it. Here's one of the craters on Earth, one of the few that still remain. And just to give you scale, there's like a, that's like the visitor center there. So this thing is huge. We'll talk more about that. Let's go and talk about the jovial planets, Jovian planets for a bit. Jovian planet is another name for the giant planets in the outer solar system. Oh, good. So Brett's been there. It is very cool. Did you go down, Brett?
No, we walked around part of the ridge, but it was very neat from the perspective of being there. It looks much more baseball shaped than it does flat, like in the images. It's much deeper.
Exactly. That's right. That's right. No, it's pretty cool. I got to go down inside it. It was pretty awesome. All right. Whoops, wrong way. So remember, one of the features we learned about the outer solar system is that not only are the planets much bigger, but they also have a lot more moons. And the nebula theory actually explains that very well. Again, a lot more gas and dust out there once the solar wind turns on. Also, a lot more material to make inner cores that were more massive, snow and ice. So the cores of these planets got bigger, and they were able to suck in all this hydrogen and helium through gravity. But that any little kind of motion around them kind of would form a moon. So these outer planets are kind of like miniature solar systems themselves, with with Jupiter being the sun and the tiny moons orbiting around that. We cannot, however, explain the size of our moon that way. Again, our moon is way too big for this process to have happened. What's going on here? There's a couple of captured moons of Mars. These look like asteroids. They're tiny compared to Mars. And our moon also could not have been captured. It's just too big from there. And so we're still left. The nebula theory still can't quite tell us why our moon is so big. That's one of the, it can't really tell us why Uranus is on a weird tilt either. It has a hard time explaining these exceptions to the rules. It turns out that we need to learn this from another star system. And that other star system, I don't know if we have time to watch this video. Probably not. Wait a second. Yeah, we can watch this one. So let's watch this.
Haute-Provence Observatory, France. It's here that a discovery from a faraway star gives one of the biggest revelations about our own solar system. The story begins when Swiss astronomers Didier Queloz and Michel Mayor noticed something unusual about a star 50 light years away in the constellation of Pegasus. Everything about this star is ordinary. A main sequence mid-life yellow dwarf, just like our sun, but with one strange difference. The star at Pegasus 51 is rocking back and forth. It's a weird anomaly astronomers have never seen before. They check their instruments. Everything is working, including their new spectrograph, a device that splits the starlight from Pegasus into rainbow colors. Hidden inside the colors are patterns of lines. By tracking the day-to-day movement of these lines, astronomers make a startling discovery. Pegasus 51 has a planet. But no one has ever seen a world like this. It's half the mass of Jupiter, yet it's extremely close to its star, 9 times closer than Mercury is to the Sun. The planet at 51 Pegasus must be inside the corona, broiling in temperatures over 1,000,000 degrees Fahrenheit. Soon, another planet is found around another star, and then another, and another. Astronomers have now confirmed over 3,700 exoplanets beyond our solar system. Nearly all of them are Jupiter-class planets grazing their host star. They're a new, previously unknown type called hot Jupiters. They're so numerous, hot Jupiters challenge theories about the origins of planetary systems.
It's very difficult to make a planet close to the star because there isn't enough mass to build a giant planet very close to the star, and there's gravitational frustrations in trying to build a planet very close to the star.
Astronomy is shaken with a new revelation. Planets do not stay put where they're born. When they're big enough, they migrate. It's a process called planetary migration. And yet, our own solar system has no hot Jupiter.
So there's a little bit of an overstatement in that video. Most of the exoplanets now are not hot Jupiters. But there are lots of these objects, and as they stated, there's no way the nebula theory can explain the existence of these hot Jupiters. It's too hot down there, and there's not enough material close to the sun to make a planet this size. So we had to, but these were this concept that this Jupiter, this hot Jupiter, was formed much further out, and then as it's getting fatter, if you will, as it's eating up all the material, that kind of slows it down, and therefore gravity makes it get closer and closer to its star. And so this planetary migration, the planets that we know right now, they were not born where they are right now. And so it turns out our Jupiter almost did the same thing. It was, watch the video in our content section. That's the next video. We don't have time to watch the next one. But Jupiter, all of the planets were formed closer. Look at Neptune and Uranus here. And there were a lot more planets than what we have now. Jupiter started to come in. It got slowed down. But luckily, Saturn formed a little bit later. And Saturn started to pull on this object until we finally ended up with, just by the planets pulling on each other, we finally ended up with a stable configuration that we have right now. But we lost lots of planets. Some planets were thrown out of the solar system. Some planets were thrown into the sun. So the early solar system was much more chaotic than it is now. It's not that everything is now is in a nice stable orbit through what's called this gravitational resonance. Each one of them pulling on each other until it finally settled down. But the early stages of the universe were very chaotic, with a lot more planets, a lot more collisions, and lots of planets being flown out of the solar system. And that is, again, this is on your content section. That is, that's how the moon was actually formed. Yes. So Brett says, was our moon supposed to be another planet? That's exactly what we're talking about right now. So the hypothesis is that it's called the large impact hypothesis. And it is pretty much the accepted hypothesis for the formation of the moon right now. One of those planets in the early chaotic solar system, we even have a name for it, is called Theia, was a little bit bigger than Mars, smaller than the Earth. The Earth actually was smaller at the time. They were on a collision course. They were, Theia was one of those extra 12 or 18 planets in the inner solar system that aren't there anymore. It actually collided with the Earth. And both of these objects were pretty much vaporized. All the rock was turned into gas except for the core of the Earth. Basically, Theia was completely destroyed, and therefore the core of the Earth, the iron core of the Earth, kind of sucked in most of the material. The Earth got 20% bigger, and the leftovers kind of orbited around the Earth, and over thousands of years, gravity actually turned that into a moon. So that's our latest hypothesis on the formation of the moon. Again, there's about a 12-minute video in our content section that explains this. Shows you a computer simulation of it happening. Actually shows you one of those supercomputers. Please watch that video if you haven't already. So that's how we got our moon. Here's just another one of the models of not just the Earth and the moon. This is a model. It's called the Nice model. It looks like it's the Nice model, but Nice, it's a place in France. It's actually in the French Riviera. So if you ever want to study astrophysics, go there. It's a nice place to work. I never worked there, but I got to go to a conference there. It's pretty cool. When we see the planets are they're swooshing around. This is just the outer planets out here, and they will eventually get into the. So we're going to lose one right now. Oh, there, a collision. We made another one there. This is how we ended up with the 8 or 9 planets that we have right now. So what is the evidence for the chaotic early solar system? Again, our moon, right? It was bigger. Odd rotations of Venus and Uranus. The ages of the craters on the moon actually indicate 2 periods of bombardment. The first was when, after it collided, it had to clear its path like the Earth did. But then there was a second period of heavy bombardment where, for some reason, there were a lot more impacts from asteroids and comets. It turns out that when Jupiter was coming towards, it disturbed the orbits of the planets, the orbits of the comets in the outer part of the solar system. And when you disturb their orbits, they're going to fall in towards the sun. Well, the Earth was in the way, and the moon was in the way. And so it turns out one of the issues we had with the nebular theory was, where did the water on Earth came from? Remember, the nebular theory said that all the water got evaporated and pushed out into the outer parts of the solar system. Where did it come from? Well, about a third of it was trapped in the rocks as the Earth was formed, but that's not enough to explain our oceans. It turns out that the water and lots of organic material, and maybe even life itself, was in the outer Kuiper belt. And when those comets got disturbed, they came raining down, and there was another period, millions of years of the Earth being bombarded by these icy objects, and that ice would turn into water. So 2/3 of our water actually comes from the outer part of the solar system through these comet and asteroid strikes. It turns out that the size of Mars, remember we said that the nebular theory would say Mars should be about the same size as Earth, but because Jupiter was migrating in, it kind of used up the material that would have made Mars. It actually used up the material that would have made another planet in the asteroid belt. We can do chemical composition of Mars, tells us that it was formed in a different place and moved around. Again, the existence of Neptune and Uranus, they formed much closer to the sun. And as Jupiter and Saturn were doing their dance, it actually threw them further away. And so that's why Neptune is bigger. They kind of switched places. And then again, we learned all of this stuff from hot Jupiters, from other star systems in there. And then again, now that we had that that idea, we put those hypotheses into computer models of the solar system and run them and see how we get a stable system from that. And so the latest models say there are as many 20 planets in big sized planets in the early solar system, and then we eventually ended up with the ones we have now. Again, this is on our content page. Watch that. Kind of a summary of all the computer simulations that we have done. I'd actually, this in particular, this tells us how we made the Kuiper belt and how the Oort cloud was formed. And so all of this leads credence to our, it's based on the nebular theory. The nebular theory was a good bedrock to our understanding of how the solar system formed. But again, a good scientist, we looked at the reasons where it went wrong, and we looked for other places, other samples, and the other samples were other star systems. And we've had to adjust our theory of how the solar system formed. Nebular theory in conjunction with planetary migration explains the structure of our solar system. And then finally, remember I told you we come back to Fomalhaut B. It's gone. We've actually seen a destruction of a planet. This is what that planet looked like in 2004 and in 2006, and we can see something destroyed that planet. This is our hypothesis that it was, this is a very young star system, and it collided with another planet. Now, again, maybe this was a Death Star, who knows? Maybe the Empire blew up this planet, but our scientific hypothesis is that this lends credence to our chaotic period of these early star systems. Before the orbits all settle down, there's collision, just like a giant pinball machine where the planets are bouncing off each other. They don't even have to hit, right? This simulation, all the simulations, but the one that the quick one here, right? You don't have to hit something for the gravity to influence you. Where did it go? Just getting close enough and getting in its orbit will kind of fling you around. So, I mean, we did see one of the collisions here, but right, they kind of dance around each other. They're spinning around each other. Now, some of them do hit. We had a collision there, but you don't have to touch to be under the gravitational influence. So everything was getting swished around in the early solar system. So it was much different, more planets, not as stable orbits as what we have now. That may beg the question: are the orbits of the solar system really stable now? And the short answer to that is yes. We have a model of the solar system. That means we run it backwards to see how it started, but that means we can run it in the future as well. And I mean, there's a little instability between Mercury and Jupiter. There's like a 1% chance that it's not even 1%. There's a tiny probability that maybe Mercury will deviate from its orbit. And once that happens, once one of the planets gets deviated, it could disrupt the whole solar system. But it's a very, very small probability. For all practical, 99% probability the solar system will remain exactly the way it is until the sun changes. A preview for a couple of weeks from now. The sun will evolve, and when it does, it's going to wreak havoc with the inner planets. Okay, that's all for tonight. Any questions on this? All right. Let me remind you again of our midterm. So I heard from a couple of you. I decided on the dates that midterm will start on Tuesday at 8 a.m. or 9 a.m. I don't remember whatever I put in there. And you'll have until 9 p.m. on Wednesday to take the midterm. Okay, so you have a day and a half. Now it's only, you only get 90 minutes. You have to choose that 90-minute window in a day and a half, or 90-minute in that day and a half window. All right. So start studying, and as part of your studying, the midterm study guide assignment is open. It's not optional. It counts for 10% of your discussion. So you have to pick one of the subjects that we've gone over and give a little summary of it. I'm going to post my summary on on relativity in a couple of hours, and so you can have an idea of what's expected of you. All you need to do before Friday at midnight is just choose what subject you want to summarize. The dates on the midterm are in our calendar. The 20th and the 21st. Starts on Tuesday the 20th at 8 or 9 a.m. I don't remember, and I think it's 8. And it ends on the 21st at 8 p.m. But it's right in, it's in the calendar. Okay, that's all I have to say. Any other questions before we take off? Okay, so Friday night, pick your midterm subject. You got your, as usual, you have homework that is due on Sunday, a quiz that's due on Sunday, and we'll have a discussion question on that'll be due before class on Monday. At least your first post will be due before class on Monday. This is not, the midterm will cover next week's material. Next week's material will be the Earth. And in fact, this may well be the most important discussion question we do. So if you're only going to do one discussion question, which some of you seem to be on that path, do this one. This is the most important discussion question we will have. I should make it count for double, but I won't. I'll do that next semester. Okay, it's about global warming, by the way. So we will study global warming next week, and that will be on the midterm. All right. Okay. Let me see. Nothing else. All right. Okay, everybody. Keep up the great work. Have a great weekend. Be safe, and I will talk to you on Monday. Thanks for coming. Thank you all.